So to draw a shear moment diagram, suppose we have a beam that looks something like this. Let's get our pencil set. And maybe it looks something like that. And there's a simply supported, probably a cantilever or something. That there would be an L1 here. And then the length of the cantilever would look something kind of like that would be our L2. All right, and so we know, just real quickly, that the moment diagram and the shear diagram look as follows. So it's for a uniformly distributed load over this. The graph for each of these would look something kind of like this. So we're going to take this, okay, the shear on this would look something kind of like this, okay, and then our moment diagram, let's slide that up a little bit. Oops, I don't know why I did that. All right, we've come over and look something kind of like this. Now, the shape of these curves and the details of the values and the locations of things would be important calculations, obviously. And while we won't go into a lot of that in this series, if you're interested in how to find the shear moment diagram and the different techniques, whether it's by integration or by area methods or other construction techniques, I encourage you to jump over to our statics series, and we go into great detail on how to put all that together. But for now, we're going to focus mainly on area methods, which basically takes advantage of a relationship that exists between these graphs. Okay, so normally this is called as the W graph, which stands for load, because usually we call distributed load as W. Okay, the shear and the moment. And we know that one of the fundamental, whoa, what did it do there? The dm dx is equal to v is one of the fundamental relationships that we can take advantage of, which basically says that the slope at any point on the moment diagram corresponds to the value of the shear. And you can kind of see that, down here, that's a pretty steep positive slope. That's the biggest positive value, and then it gets flatter. So at this point, which the diagram's a little bit off, this would be my M max, right? Because if I make that equal to 0, calculus tells me that the maximum occurs where the slope is 0, or as does a minimum for that matter, but finding those locations. Okay, but there's a whole slew of information that we have to be able to draw these pictures. All right, so we kind of make a list of what it is that we need to do on there. The first one that we have to have is we have to have support reactions to get those, all right? Because there is a relationship between the support reactions, if you will, and the shear diagram. In fact, if I go through and I draw, let's make this a little bit bigger. There we go. That'll work. That we know that there's a vertical reaction there, there's a horizontal here, and then there's another vertical that happens here, that the behavior of the loading diagram directly affects the shear. And again, without getting into a lot of details, but you can see that at the location of that vertical reaction, there is a jump in shear here. And the amount of that jump is equal to that reaction. Just like from here to here coming up, like that, it's equal to that value. And so we can construct these diagrams by taking advantage of these relationships and playing with those. Okay, and then the moment diagram then builds off of the shear in a similar fashion. So I've got to know the support reactions to be able to get the shear. If you don't get the shear diagram right, you can't get the moment diagram right. Okay, all right. Now, if we come back in, the other thing that we need to know then, in addition to support reactions, okay, is that we need to know something known as the critical points of the graph. Okay, and those are places where something in the diagram changes or causes it to jump or to change direction. And there's a whole mess of points that we have to be able to take account of. And that's the focus of this video, is to be able to locate the critical points on a graph based off of only the load and the geometry. Okay, so this guy, oops, or load and geometry based. Okay, all right. So those are kind of what we're going to be looking at doing, is trying to figure out. Now, what the critical points serve to do is they're a connection between the diagram the load diagram and the shear diagram and the shear diagram and the moment diagram. Okay, and so there are several categories. If I start another box down here, okay, that the critical points fall into several categories. I need the start and end of the beam. Well, we've got those. Those were our leftmost node, rightmost node. That's why I needed those. Okay, we need all concentrated forces and moments are a critical point. So if we have a point load on there, okay, the begin and end of distributed loads are a critical point. Okay, support reactions are definitely critical points. Support right there. And then there's one other one that sneaks in, and we've kind of hinted at it already, and that's anywhere that the shear is going to cross into 0. Okay, because that location is the one that takes advantage of this guy. Okay, that's the location of our max and our min. So we'll have to come up with an algorithm that is able to analyze our shear diagram and figure out where are my zeros. And so we'll have a methodology that says, hey, and we'll come up with ways to get that value. Okay, but those are the 5 classical critical points that we have to have. So so you can see we've started kind of setting up for this already. Like we've got number 1 done already. So that one's done. Okay, I know where all the concentrated forces and moments are. That's in the load definition. Beginning and end of distributed loads. We kind of did a little bit of that when we were drawing the loads using our methodology there. So that's what this is what's getting me our D1, D2 values, get me that guy. Okay, this guy, I just need D1. Okay, support reactions. Well, obviously we know where the support reactions are. Okay, we did that with our support types flag on that one. Okay, and then the only one that's left to figure out is this V equals 0. So the mission today is to be able to try to, on a graph or a picture, get lines that will show up to represent all of these. Now, for the example that we have shown here, let me change my color a little bit. Let's go to, say, a green so you can kind of see stuff. Okay, if we go through and draw down from, pull that up a little bit, from our beam on this, we can start to kind of lay in these lines. So I would need a line that goes from here all the way down. Okay, and I know it's a little low. That's a start and end of a beam. That's that guy. It's the start and end of a distributed load. That's a 2. Okay, or sorry, a 3. Okay, it's also a 4. Okay, so there's a lot going on that one. Okay, other critical points that we have. Let's see, start and end of the beam. So we need one that's over here. That's that guy. So that's a 1. Okay, all concentrated. We don't have any concentrated forces and moments, but say we had a moment in the middle of this, then we would have a line that comes from that as well. Okay, the beginning and end of the distributed load, so that's also a number 3 there. Support reaction. Okay, well, support reaction's at a different location, so I need one that comes down here. Okay, and so that's a number 4. Okay, and then V equal to 0 is the last one. Well, obviously, V crosses 0 here. Okay, and it also crosses 0 here. Okay, so this is a number 5. Okay, and then this one, if I come down through here, and again, my curve's a little bit off, but that's supposed to be the end max point right there. Okay, and that would be a number 5 also. So we need to come up with a list of where on the beam those points are. And so we'll come up with a strategy to be able to solve this. So I think what we're going to do is we're going to build an array, and we're going to search our data, and we're going to plug all of these in to be able to get our critical points, and that's the objective. Once we do that, then we'll do just a quick drawing, and we'll draw some vertical lines to represent what these are, and then we can kind of play with our diagram and see if it can pick up what all of our critical points are for the distributed loads. But that's what we're got. So with that all set up and kind of a basic, kind of where we're going viewpoint of what a critical point is, that's what we're looking at. Apologize for the graphics, a little rough. But again, if you need more information on this, take a look at our statics playlist and go look at the ones on drawing shear moment diagrams or shear and moment relationship videos. I'll put a link in the video for you to be able to find those, and we will be good to go. So, all right, well, so let's jump over to the code. All right, so here we are in the code. And just to kind of catch you up on where we're at, so far, we have the ability to be able to draw beams. And we've been working on, in our last video, we did some logic on making sure that loads didn't exceed their bounds. We've got some temporary test lines that are happening here, and kind of how we're starting to kind of work our way through this. Our goal is to be able to take this beam and locate the critical points. And what we will do is we will now take, and as the first segment showed, is we're going to try to draw vertical lines at every critical point on the beam, but we need an algorithm to be able to determine where the critical points are. So that's our goal on this. Okay, so the first thing that we need to do as we get in here is we need to come up with a way to house our critical points. All right, so I'm just going to add, and again, just for lack of a better idea, we're going to kind of work on having we're just going to use lists. It's just the easiest way to do it. I know you could do, observable collections and, and those kind of things that auto update drawings and do stuff like that. But I'm not, like I said, we're just brute forcing this at this point. We're going to do a list. And now this list, though, is going to be a list of nodes. Okay, so we'll have to make some temporary nodes in there to help us as we kind of work our way on this. So that should be a single node, VM node. And we're going to call this as critical points. If I could type today, that would help. Let's do a get, a set, and we're going to make that equal to null initially. Okay, and then we're going to come in and we're going to kind of look at doing some of these things. Let's see. Some other cleanup stuff that we can kind of look at doing as well. But for now, we're just going to work on getting our thing. I've kind of worked through this already. So what we want to do is we need to create this list, and that's our big challenge. So yeah. So we need to, so we've initialized it. And so where am I going to put that? That sounds like a good spot. Current mouse location right here. It looks good underneath add node. So let's do a protected list of VM nodes. Okay, and we're going to list critical points. Will be our helper function that will contain our logic to be able to set this up. Okay, first thing that we're going to do is we're going to make kind of a temporary placeholder as we search for eligible candidates. Okay, and this is a new list, a VM node. That will get us there. All right, and then at the very, very end, what we're going to do is we're going to return the list when we're done, and that will give us our list, and then we'll assign into that our critical points. All right, so if we go through our list of 5 objects, we need support reactions. That's an easy one to find. I need concentrated forces and moments. I need the, see, up in here, support reactions are easy. Let's do the begin and end of the beam. This is our leftmost, rightmost. Okay, concentrated forces, and then I need begin, end of distributed forces. Okay, and that will get us that one, and then I need shear equal to 0 will be one that we'll have to, and we'll have to kind of address that one a little bit later, so we won't do that one right now, but to do shear equals 0 critical point location. So for now, there's not much we can do with it, but we'll come up with that one as well. Probably that one's going to take a little bit of work to analyze, so we'll probably add that one in a later video. All right, so that gets us our parts. Okay, so let's do support reactions first. Okay, so for each, and we're going to do VM node item in nodes. Okay, that will get us for each. Man, fat fingering today, aren't we? That will get us that. Wow, I'm still fat fingering. Let's try that. Better? Okay, thank you. Whew. Cancel the recording. The man can't type. Okay, so, all right. So if item dot support type is not equal to support types dot, and then the undefined, this would be those free nodes. Okay, basically, if it's got a roller condition or a fixed condition, then we know it's a support. Okay, and then what we're going to do is right off the bat, we're going to list.add item. So we know that if it doesn't have that, it's got to be a support, it's got to be on the list. Don't have to check anything else. We know those points are unique. We're good to go. Okay, so that will get us that. Okay, the start and end of the beam is fairly straightforward. Okay, and basically now here's the problem. As you saw in the diagram that we had before, I could have critical points from multiple categories occurring at the same point. So now for every other critical point that we're looking at, we have to go back and look at our list and see if that list already contains that node. Okay, so if, okay, not list dot contains our leftmost node, okay, then all we're going to do is list dot add our leftmost node. Boom, got it. Okay. And then if not, and you can imagine what the next one is. If not list, wow. List dot, wow, come on. Dot contains rightmost node. We can do a list dot add our rightmost node. Okay, so that gets us into those. So lots of little chunks for finding our critical points. Let's see. Now, we can almost start factoring these out, because maybe at one point we want to have a way to grab all our support reactions. Well, that's an algorithm to do it. But again, for now, brute force, just get it up, get it working. Okay, so for each, okay, now in this one, we're now going to start looking at, oops. I don't like my print screen button being right by my backspace key. Okay, so for each, and then the VM base load item and loads. Okay, that's going to be, so we're going to go through all of the items that are stored in our loads array, since we've added loads. Okay, so the first one that we're going to look at is our concentrated forces or moments. Okay, so first thing we got to do is we got to go through that list and pull out anything that, if it is a concentrated force or moment. So item dot load type is equal to load types dot concentrated force. Okay, or item dot load type equal to kind of the same thing dot. And then we want concentrated moment as the next one. All right, and that will get us that. Endpoints the same. Okay, and they should be, since we put the validation in this. First time I worked through this was before the validation. If it's a concentrated effect, okay, so we're gonna make a node, okay, based on the location of the load. So again, these are concentrated effects. They're singular values at singular points. Okay, so here we go. So again, it should pass this every time thanks to the validation, but we're going to put it in just in case something goes squirrely on here, equals item.d2. All right, and once we're in there, the question is the load at the start node? That's the first thing we need to check. Okay. Okay. Or is it at the end node? Because those nodes are already on the list. Okay, so case one, it's the start node. So how do we know the start node? Well, that's just if item.d1 is equal to 0, because we measured everything off the left. Okay, then this list.contains.beam.start. And oops, not dot. That's a parenthesis. Okay, and then we're going to add the node. So if it's at the start, dot add item dot beam dot start. We'll get us that. List contains, wow, item dot beam.start. Okay, there we go. Then, so now again, okay, if it doesn't already have the start node in the list, which would be in the case of like a left cantilever, okay, although technically that's probably already there, but that's, I don't, well, like I say, we may not need this. I'd have to think about that a little bit more. Okay, otherwise, because it's the end node. Okay, so how do we figure out if it's at the end node? And we're going to do an else if here, because it can't be both. Well, if there's only one node, that could be a problem. But let's go in, and we're going to do now math.abs. We're going to do item.beam.end.x minus item.beam.start.x. So that's measuring the length of the beam. Okay, and if I go through and I do that, okay, if that value is the same, now we can basically take this chunk where we're checking this and throw that in there, and this becomes an end, and this becomes an end. Okay, that's our second case. Okay, otherwise, okay, it's in the middle somewhere. Okay, so make a temp node and add it to our list. Add it to the list. Okay, so that's what we're going to do. But first we got to check, check that the new node isn't already in the nodes list. Okay, which hopefully it's not, but I guess if you had a distributed load that was already in there and a point load at the start of a distributed load, I guess it could be. So, all right, so then we'll do else. Okay, and now we're going to do a little bit of logic. On here, we're going to do a double, let's call it temp x equals item.beam.start.x, okay, plus item.d1. So that gets us the distance from the start node that we want. Let's see, and then we want to do double temp y is item.beam.start.y. Okay, and now we're going to search our current list, make sure that it's not already on there. So let's make a variable node found equals false. Okay. Let's see. Okay, since the nodes are only beam, so yeah, so we need to do a for each. Oops. For each VM node in nodes. Okay, if n.x equals our temp x. Whoa, why did you not? Our temp x. Okay, so a node at this point, okay, has the same x value. Okay, so but again, if we have points that are arranged vertically, then we need to check if n.y equals temp y on this for our case. Okay, then the node is found. It's going to be equal to true. Okay, and then we will break out of the search because the node's already in the list. We don't need to search any further. All right, so that's our for each. Okay, now after that, then all we do is if the node wasn't found, so if not node found, okay, then we're gonna do do I need list.add new VM node? Oh, let's do a VM node new node. I know I'm mixing my camel cases and all that kind of stuff. But our new node is equal to a new VM node consisting of temp X, temp Y. So we need to, because we need to put that on. So there wasn't a node in the nodes list for it, but we do need to check, and this was, I see, a minor error in the code. I need to do this again. List.contains if node isn't found. So this was, we made a node in the nodes list. I'm trying to think here. But how do I check? Now we need to go back. Well, if it's not in the node list, do I need to do, let me think here. Take the same code, and this time in list. Because if the point's already there, I don't need to do it again. I guess I could just draw it a second time. By there, just put multiple entries into the nodes. That's going to be kind of an... let's check the list again. Alright, so we dropped, so if we have true here, node found. So if it's here, then I need to check here. Let's reset it. Node found equals false. Yeah, here we go. I'll throw this into here. Bool. I don't need to redeclare it a bool because it's already been found. All right, so now we're going to search. So we searched nodes to see if the node was in there. Now we're going to search the list. Got to be a better way to do this. A list again, okay, and then if that's not what I want. All right, so what we can do here is we're going to take our new node. We're going to move it up to here. Okay, and then we're going to break this out. Look something like this. We're also going to have, basically, this is the problem. So VM node temp node is equal to null on this. So we're searching to see if there is a node already in the system with those coordinates on it. Okay, so if the node is not found, we make a new node. Otherwise, so we'll assign that to temp node equals new node. Gets us that one. Otherwise, we node found, and then temp node equals n gets me that one. So this is where, so we found it, we assign it to the temp, and then temp node equals new node. Yeah. Now can we... temp node. They don't want to make a node if we already have a node. So that's otherwise, yeah. Otherwise, I'm going to leave the else here, do nothing since it was already, since temp node was already set. Okay, so that gets us to that. Okay, now we can go through and for each VM node in the list, now I can say node dot x parameter, does that match our already stored list of nodes? And then this guy is temp node dot y. And I see some refactoring. We're doing the same logic over and over. So we'll pass it a node, pass it a list, say, are you in there? And we'll just return true or not. But we'll refactor that, but I already see, you can see it kind of, a lot of that work's coming through. Okay, so that will get us to that. Okay, and then we can do temp node here. All right, sorry about that. Okay, a little bit of logic check. I had two lists I had to check. Okay, so that gets us there. So let's label this search our critical point list for a node at this location. Okay, and then this search our stored list for our nodes list for a node at this location. So yeah, so if it's already got a node in here, we know there's a node, I can check for it in the list. Otherwise, we're going to make a new node and then check for something that matches the coordinates at those. Okay. And so basically, once we get through all of that, if our node found, am I getting ready? And just because I'm a little nervous about overriding, this is a different node found search. Because I would have failed that check every time. Node found 2. Make that a node found 2. We'll make you a node found 2. There we go. And now we won't have to worry about resetting our list, in theory. Okay. So that gets us that. Okay, now we can go in and start finding. So that was our concentrated forces. And that gets us to here. Okay, now that's this guy. Let's see. Okay. Else. Okay, if item dot load type is equal to a load types dot distributed force, or item dot load type equal to load types dot distributed moment. Like I said, I don't know how often that will be used on there. Okay, then we kind of play the same game. Okay, now in this, again, just in case, originally when we set this, I didn't have all the validation in, but if D2 is greater than D1, which it should be, D1, so we're checking, okay, if the end of this, our distributed load is to the right of the start of the distributed load, all right, then we kind of play a similar game. Okay, first question. 1, is the start point at the beam's start node? Okay, so we're going to check if item.d1 equals 0. Okay, and then again, if not list.contains item.beam.start, we're going to list.add item.beam.start. Okay, otherwise it's not at the start node. Okay, and we're going to kind of play a very similar game. Okay, and I think we basically play this same game again. Yeah, so this check, yeah, we will definitely do so. I'll refactor this off screen. Control C. And we will drop that in there. So it's basically the same set of checks. We're now checking our list. Let's see if the point's already there. We're also checking those. That gets me that guy. Is that? Okay, so that gets me to the start point. Okay, and so then the next check that we need to do, which will go here, is basically a similar thing. So number 2 is the endpoint of the distributed load at the beam's end node. All right, and so if item.d2 equals, again, we're going to math.abs of item.beam.end.x minus item.beam.start.x. All right, and then we're going to check if not list.contains item.beam.end. We're going to add it to the list item.beam.end. It says that. Okay, otherwise we're playing the same game for all of this stuff. So that same check yet again. And we can throw that here. Except now we're doing start.x plus item dot. This is a D2. And then everything else should be the same. So that adds our temp node. Okay. And again, like I said, it's a bit lengthy because we're repeating a lot of the code there. So the first one is for start, so we need D1. Second one is for the end, so that's why I need D2, but everything is built off of the start. And then that will get us there. Like I say, I think we're going to refactor that out. But again, I'll do that off screen, and then I'll catch you guys up in the next video on those particular changes. All right. Let's see, what do we need to do? Okay, so let's run that. We're not drawing anything. I just want to make sure that it compiles, that we didn't blow something up. All right, so we're still good. So now what we need to do is we need to come in and for now, let's go to on user create, user update. And at the bottom of this, now that this is where we created our beam, we could do critical points equal list critical points. Okay, so that's where we compile the list. And then on user update is where we will actually do something with it. Okay, so we're going to add that to the end of on user update. So draw the lines for the critical points. Okay, and so for each VM node item in critical points, we're going to do a drawing helpers dot draw line. We're going to put that onto the main canvas again, just like we've been doing before. And now I'm going to do item dot x and then item dot y. For now, we'll just drop it 50 below the node points on the beam. Again, these hard values, item dot x, item dot y, plus this do a ridiculous number for how far down to draw the graph. Again, that will change, but we're just checking to see brushes dot, let's make that, we like our green color. How about a dark green? That'll look good. Okay, and I can do that. All right, so with any luck, we should start getting a bunch of green lines at the critical point locations of our beam. And if you look, that is indeed what we have. Okay, so you can see that, again, as our critical points go, we have our support condition. So that's this one. Okay, and I really don't like that color. Let's instead of dark green, let's just make it regular green so we can tell the difference between it and the supports. Try it again. A little better. Okay, so critical points, support conditions, one there. We have one here, got it. Okay, starting into the beam, got it. We have add a point load, got it. Beginning and end of the distributed load. So here's one distributed load, 1, 2, got it. And then there's probably a second. I don't know if there's two lines here. So there's that distributed load, here's that distributed load, and here's that one. So it looks like we're finding them. Now let's make a couple of other cases for our beam. Let's make another, add another node. VM node D is a new VM node. And we'll put this guy out here at, say, 750, at 200. Support types dot undefined. So that gets us a cantilever. And then we're going to add another beam, beam 3 is a new beam, and we're going to go from my third node, from node B to node D. Gets me that. All right, so let's see. I should put a cantilever on the right end. And what did I do? Oh, forgot to add it to our list, didn't I? Beams.add beam 3. Okay, I also want, I need to add node D here. Gets that one. In fact, we're gonna make another one on the left end. Node 120. Let's just go from 50. That guy, we've already got a D, so make that an E. Control C, and that shouldn't be beam 1, that's a beams. And then add another beam for a left cantilever. Again, just making some test cases. 4, and we're going to go from E to A. Beam 4, got it. Okay, we got our point load. I want to move this so that it's at a different point. So let's make that like 50. 50. And if I run that, ooh, what did you blow up on me at? Oh, I did again. Beam 1. This should be beams. All right, start that. So now you can see we're starting to get. So here's our cantilever. Probably do need to draw a node at supports just so we can see it. Okay, so started beam, check. Support, check. Distributed load still. Point load, check. Check, check. And then looks like it's working. You can kind of see if I pull that down. I think we got it. So those are our critical points. And so what will happen is now that we have the critical point list, as I start to clean this up and we start to calculate values, each one of these points becomes a part of a picture that is a different free body diagram that we will resolve, and we'll come up with the algorithm to be able to work that next. So we've got our critical points figured out. So that's the start. Now we'll make those, again, we'll change the line types, maybe make it a dotted line or something faint just so we can see stuff. But that's pretty stinking cool on those. And so that's how we're picking up all the points that we want. So I think, short of anything that I've overlooked, I think that will get us where we want to be. So there we go. So anyway, yeah, they're your critical points. So that's the first major step in drawing the shear moment diagrams. We've got all the points that we need to be able to set up the method. And in our next video, we'll start doing some calculations. And then, I don't know if it'll be that video, but the next one after that, we'll actually start coming up with ways to draw that diagram to scale on our shear diagram. And that's what we're trying to work on. So anyway, thanks for coming out. We'll keep on working on this, and slowly it'll evolve. It'll get faster and better. And I will clean up the code off screen, and then we will do some refactoring and kind of clean some stuff up. There are a couple other things I want to, minor changes I'll tweak, but I'll catch you up on that on the next video. You know, you don't need to see me watch me refactor a bunch of code. So anyway, thanks for coming out. We'll see you guys next time. As always, if you like the video, give us a big thumbs up and toss us a like or subscribe to the channel, and that will let you know when the new videos drop. So have a great day. See y'all. Bye.